I want to go into a tricky big data example. And for this function, we have a tree recursive function. So, and this function looks very similar to another function we've seen, and I think you'll notice it, but we'll get back to that, don't worry. But anyway, let's figure out the runtime of this function. And this function is going to be a little tricky to figure out because now we're going to have to look at the tree to figure out how the function calls work. So the tree for this function, the cascade of recursive calls, looks as such. So each time we're going to go down the tree until we reach the base case, and they're going to return. So this is what the tree looks for n equals 4. There ends up being 15 calls. So again, our cost model for this recursive function is going to be the number of function calls. So for n equals 4, we ended up getting 15 calls. Now, what about n equals 5? So see if you can draw the tree for n equals 5. You can actually basically reuse the n equals 4 tree and add something else. So what you end up getting is this tree, and I actually couldn't fit it because it was so big. But basically, we have f of 5, and we go down to f of 4, and these trees we've already seen. So each time we go, we end up, so from f of 4 to f of 5, we have to evaluate f of 4 twice. So that's 2 times the number of function calls, and then we had to add one more. So in this one, we ended up getting 31 calls. So in the previous one, we had 15 calls. This time, we had 2 times more plus 1. So this is an interesting pattern that we're seeing. So let's see if we can figure out what the general big data runtime of this function is. So the way we can do this is we can kind of map it out. So if we have input size of 1, we're basically done. If we have input size of 2, we have 3 function calls. If we have input size of 3, we have 7 function calls. 4 has 15, 5 is 31. So now, if my question to you is, if we have an input size of n, how many function calls can we expect? So I'll give you a moment to think about that, and after some thought, you might be able to find that this has 2 to the n minus 1 function calls, and you can verify this by looking at each of the inputs and the result. So what does this mean? What's the big data notation runtime of this function? It's just theta 2n because we eliminate the lower term, the lower order term. Alright, so this ends up being an exponential time function, and we know from what I told you that exponential time functions really suck. So this is going to now lead us into our next discussion. So you might have noticed that this function looked very similar to Fibonacci, and because it looks so similar, we actually said true recursive Fibonacci has a runtime of approximately theta 2 to the power of n. Now, if you remember from the beginning, from early in the course, we tried to evaluate we tried to put fib of 30, and it took the function quite long to figure this out. And the reason it did that is because the runtime of this function is 2 to the power of n. So that was one of our first encounters with efficiency, and this is why it was so slow, because this is an exponential time function. Now, notice that I say it has a runtime of approximately theta to the 2n, because even though this function looks very similar to this function up here, so even though it looks very similar to this function, it's not exactly the same because we have that pesky n minus 2 here. And because of this n minus 2, the actual runtime of this function, for those of you who are interested, is something that looks like this. It's called theta to the 5 of n, where phi is equal to 1 plus square root of 5 over 2, which is approximately 1.618. Now, this number may seem a little familiar to you because this is actually the golden ratio. And the golden ratio is one of the coolest things in mathematics. I highly encourage you to look up and see some of the cool properties of this golden ratio. And the Fibonacci sequence is closely tied with the golden ratio, and it's actually interesting because the golden ratio shows up in the runtime of this tree recursive Fibonacci. And the tree recursive Fibonacci, remember, is basically the definition of the Fibonacci sequence. So this is some crazy connections here in this one slide. So I personally think this is really cool. I really like to see connections between things. But anyway, I'm actually not going to go into the math that shows that the runtime is this because that's a little out of the scope. But if you're interested in that, I highly encourage you to look it up because it is really cool stuff. But anyway, back to the problem at hand. So we know Fibonacci sucks. So it kind of doesn't make sense that the definition of Fibonacci should lead to such a bad function, you know? Like that feels wrong. So our question now is going to be, why is it that tree recursive Fibonacci is so slow? And is there any way to improve it? So now let's look at the Fibonacci tree. So Fibonacci tree is going to first calculate fib of 4, and it's going to go all the way down this tree, calculate all of these, and then now it's going to go to the right side of the tree and it's going to calculate the respective recursive calls here. But notice something interesting. fib4 is calculated twice. So it already went through the process of calculating fib4, and then the function kind of is being stupid again and saying, hey, I'm going to calculate fib4 again for no reason. Like, can I just remember this? So this is an important idea, and this is why this function is so inefficient. And it turns out that it also calculates fib3 multiple times. It also calculates fib2 and fib1 multiple times, although the fib2 and fib1 cases aren't as impactful because they end up just being return statements, the base cases. So this doesn't matter as much, but the fact that it's computing fib3 and fib4 again, well, I mean, that makes me mad. Like, why are computers so stupid? Like, shouldn't it remember it? So now this is going to lead into our next topic, which is called memorization. And so we can actually make computers a little smarter and tell the computer, hey, whenever I want you to remember something. So memorization is the process of remembering previously computed values. And so memorization is going to actually end up creating a much more efficient Fibonacci sequence. So now let's look at this. So I'm just going to go straight into the memorization definition. So this is going to be a memorization function. So we have the Fibonacci sequence right here. Okay? And now what I'm going to do is I'm going to define a memorized version of f. So I'm just going to go through this definition. It's not too hard to understand, but it's something you'll develop with experience. But basically, this is going to be a higher order function, because what we want to do, the goal of this function is we want to pass in Fibonacci in here and get a faster version of Fibonacci. So what we're going to do is we're going to define. So actually, I'm going to define this as memo, so it's clear, because I want to return a memoized function. So now I'm going to define my inner function as memoized. And now inside here, we're going to pass in the input. Okay? And then we're going to return the memoized function. And so what should this do? This needs to find some way to remember. It needs to have some type of notion of memory, right? So what I'm going to do is I'm actually going to define, so this is the key idea here, and this is, I'm not expecting you to define this function on the fly, because this is something that you just kind of have to learn. Like, it's kind of really hard to figure this out on your own. But so don't feel bad if I'm just handing you the answer here. But basically, you're going to have to define a memory, a notion of memory, and we're going to define that as a dictionary. Because what we want to do, the idea is that we want to map. So the whole problem is that we were computing previous values again and again. So what we're going to do is we're going to map a key that's an argument of the fib function to its computed result. So whenever we compute the result of a Fibonacci call, we're going to store that here. So like if, for example, fib of 3 returns 2. So it should be the case that 3 is going to map to 2. So if we, instead of calculating fib 3 again, we can just look up the value in the memory and get it. So now once we have this idea, the actual logic of the memorized function is not too bad. So if it's the case that my n is not a key in the memory dictionary, so it's basically not in the memory, I need to update the memory. So because now I've encountered a new value, so I need to store this in memory by doing memory of n is equal to whatever my Fibonacci function call returned. So remember, we're passing Fibonacci into this here. So what I'm going to do is I'm just going to calculate f of n. So now we actually have to evaluate the function, and then what we're going to do is we're going to return whatever's in the memory. So now we know it's stored in the memory, and we just return the memory. And if it is in the memory, it's just going to go straight and return whatever's in the memory. So now let's see how this improves Fibonacci. All right. So remember, so we have a fib function right now, and this fib function is very slow. So this fib function, if I pass in something like 30, it's going to take a while to compute the 30th Fibonacci number. So, and if I put something like 32, it's going to take quite a while. So let's give it some time. I just want to show you like the degree of time that this takes to calculate this value. Like, it did a lot of computation for that. And if I pass in something like fib of 40, I would have to be waiting here for like probably 10 minutes before it returns the value of that. So now the question is, can we make fib faster? And now we've basically defined a way to do that. So what I'm going to do is I'm going to make my fib function a memorized version of the fib function. And now watch the magic happen. I'm going to do fib 30. Remember how long that took? Instant. Remember how long fib 32 took? Instant. Now, can you imagine even putting 100 in the previous fib function? Instant now. And now let's just for fun, fib 1000. Oh man, it's instant. So notice that this is pretty cool. Like, because of this definition of having a memory, we've increased. It looks like we've increased the speed by a lot. But how fast have we really increased the speed? That's the next question. So why is memorization faster? That's the question we're going to try to answer. So to demonstrate this, I'm going to highlight in red an actual function called to fib, and then the green highlights are going to be the ones that we found in the memory. So when we first evaluate fib of 6, in the tree recursive version we have to evaluate all of this. But now in the memorized version, we have to first evaluate fib of 6, so that's one call. And then we're going to go to fib n minus 2, fib of 4. And when we go to fib of 4, we're going to go to fib n minus 2 again, so then that returns that. So we've computed 6, 4, and 2. And then we're going to go to fib of 3. Fib of 3 is not in the memory yet, because we haven't computed 3, so it has to calculate that. And now it's going to go to fib of 1. Fib of 1 is also not in the memory, but that's just the base case, so we compute that. And now, when we go to fib of 2, notice that we already calculated fib of 2. So this is drawn from the memory. And then we're going to go to fib of 5. And then once we're there, we go to fib of 3, and fib of 3 is in the memory. So it turns out that we don't even have to go to fib of 1 and fib of 2, because we've already computed fib of 3. And then the greatness really happens here, because now we've calculated fib of 4, so we just pull it from the memory. And then we don't have to do any of these calls down here. So how many function calls did we end up doing actually? So previously, in fib of 6, we had quite a lot of function calls. Now we only have 1, 2, 3, 4, 5, 6. So six function calls for an input of 6. And actually, you'll see that by doing the memorized version of this function, we changed this from an exponential time function to a linear time function. And that is why fib became so much more faster. So anyway, memorization is a really, really important topic. And this is how you can make functions more efficient. Because remember, earlier in the course I said, hey, just because this is a case where recursion is pretty slow, but using recursion, we can still use recursion, but we sometimes have to memorize things, so to prevent it from computing things over and over again. So this is why memorization is faster. And from this video, I really want you to take away the big ideas of efficiency, how we measure efficiency, and go through a lot of big data examples, see if we can figure out runtimes of functions. I'll be doing a lot more practice on that later, but really, I think efficiency, honestly, is one of the most important topics in computer science. And I know I say that about a lot of topics because I think they're all important, but efficiency really is important because, in my opinion, efficient programmers are the ones that are actually great programmers versus those people that hammer out the code. Because once you start thinking about efficiency, you actually really analyze your code and see if you can do things better and faster. So, and efficiency at the end of the day, if we didn't have efficient programming, things like Google wouldn't be possible. Things like all the amazing technology we have wouldn't be possible. Like, they have to figure out efficient algorithms to solve these problems. And efficiency is something we're going to talk about a lot more in the next part of this course series, which looks at data structures and algorithms. But this is a broad introduction to it, and you also see a technique to make things faster. So anyway, thanks for watching. I hope you enjoyed this video. Again, this is one of my favorite topics, so feel free to if you have any questions, ask in the comment section. I'll talk to you later, and I'll see you next time.